So far in our chapter on redox and electrochemistry, we've talked about what it would take to make a good battery. Can I harness the transfer of electrons between two spontaneous redox reactions to 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 make a battery to get some electricity to electrical energy out of it? The opposite is also an important consideration. That is not using electricity not wait, not using chemistry to make electricity, but using electricity to make chemistry. Not using spontaneity to produce the flow of electrons, but forcing a flow of electrons to produce something to happen that wouldn't normally happen. It's called electrolysis. It's used in industry quite a bit. In any case, the setup is something like this. I have a strong battery with a lot of electricity, and I push electrons backwards through a system that normally wouldn't like to run this way. For example, if I had a hot, dangerous molten sodium chloride bath and I put electricity through it, what ends up happening is the sodium ions gain electrons to become purified sodium, and the chloride ions lose electrons to become purified chlorine gas. Such a thing would never happen all by itself because it's just not spontaneous. We could calculate the free energy for that, the equilibrium constant for that, the cell potential for that, all three of which would say, no way, Jose, it's not happening. The reactions would look like this. Chloride ion giving up 2 electrons, or giving up 1 electron and 2 of them. Sodium ion gaining an electron to become purified liquid sodium. I say liquid sodium because it's so hot it would melt the sodium, but it would kind of pool and probably sink to this bottom of this container. Kind of a scary proposition, especially considering chlorine gas is so nasty. You'd have to do it in a controlled environment. But indeed, this is how they make, on occasion, pure sodium, and pure chlorine. They make a lot of pure elements, or purify impure elements with electrolysis. They're called electrolytic cells. They're forced, and we have 2 electrodes, an anode and a cathode. It's a lot safer to do this in water, so you don't have to get things super duper hot. But if there's water involved, then the mitigating factor is the water itself can either gain or lose electrons. Do you remember this? There's an equation on the sheet of reduction potentials that says I can take water and add 2 electrons to it to get a reduction, and there's a voltage for that. It's not spontaneous, but you could do it. Or there's an equation for water giving up 4 electrons to become oxygen gas and 4 hydrogen ions, and that's not spontaneous either. But still, if either the E of reduction or the E of oxidation of water is more positive, or i.e. less negative than the reduction and the oxidation you're alternately considering, then this one might happen, or this one might happen, or they both might happen if there are ions in solution that really don't want to get reduced or oxidized. So for example, if I was trying to pass electricity through sodium chloride solution of water, I'd have to consider the following. So would the sodium ion like to gain an electron? Here's the E of reduction for that, because it's reducing because I'm gaining a negative electron. It's not very likely, negative 2.71 volts. Or would water like to gain 2 electrons? And that number is negative 0.83 volts. So which is less negative, i.e. more positive, the reduction of water or the reduction of sodium ions? Aha, it's the reduction of water. So at one electrode this wouldn't happen. I just break down the water. And on the other electrode I have perhaps the oxidation of chloride to become chlorine, or the oxidation of water to become oxygen gas and hydrogen ion and giving up 4 electrons. And the question is, which is less negative? And the answer is this one is less negative, but only by a little bit. That's why if you look at some sources, they'll say that at the other electrode I'll see this reaction happening. And in fact, some of the bubbles that come up off the electrode, most of the bubbles probably are oxygen gas, but I bet there'd be at least a trace amount, I'm not sure how much, chlorine gas there would be. But so doing electrolysis in water, always a little bit complicated and mysterious. If it's not too unsafe to try it, you just try it. Put a 9-volt battery, attach it to some electrodes in the aqueous solution you're curious about, and try to analyze the product you get. Interesting. Yeah, this picture says just what I said, that I would get the reduction of water to hydrogen gas and hydroxide. I said you probably would have the water oxidizing, but this source says chloride oxidizing. I don't disagree. I see some of that because the numbers are so close. But in any case, you got to think about it. What about sodium sulfate, for example? Sodium sulfate, I could look at that, or you can just go back and look at it later. Sodium ion gaining an electron to become purified sodium really wouldn't happen aqueous anyway, because then you'd be producing a water reactive compound, sodium, and it would react with the water. So that doesn't seem very likely. And the sulfate ion is just so darn stable that you're not going to be able to oxidize that very easily. Instead, the water will oxidize, and at this electrode, instead of the sodium ion getting reduced, I'm going to see the water get reduced. Did I write those equations separately again? Well, anyways, this is less negative than the sodium ion gaining an electron, and this is less negative than the sulfate ion getting oxidized. Maybe I didn't even write down an equation for that. Shame on me. In all electrolytic cells, the most easily reduced species is reduced, and the most easily oxidized species is oxidized. And by most easily, I mean more positive, i.e. less negative. So I think I'll show you this demonstration in class for sure. If I take potassium iodide in water and pass electricity through it, what will happen? Will the potassium ion like to gain an electron to become purified solid potassium? You already have a hint, because potassium and sodium are in the same family and they're both water reactive. That's going to be a fairly negative cell half reaction, reduction half reaction. So obviously the water gaining an electron is less negative, and this is the one that's going to happen. I'm going to see some hydrogen gas and some hydroxide being generated. On the other electrode, I could say, is it likely the iodide would give up electrons to become iodine? Or the water, again, giving up electrons to become oxygen and hydrogen ion? This is quite a bit more negative than this, so I'm going to say the iodide is more likely to happen. It's negative, not spontaneous, but I can force it more easily than I can force this. Interesting. What if I had some tin 2 chloride? Here's tin 2 gaining 2 electrons, or water gaining 2 electrons. This one, the cell potential, the standard reduction potential is negative 0.14 as compared to negative 0.83, which is less negative, so I'm going to go with this one. And I'm going to show you this one as a demonstration as well. On the other electrode, you have chloride losing electrons or water losing electrons. Which one's less negative? Looks like this one, but only by a little bit. So again, I'm pretty sure I'd see mostly oxygen gas being generated because it's less negative, i.e. more positive, but I might also see a little bit of this happening. Electrochemistry is kind of complicated. It's fun though, interesting once you get the hang of it. Here's the overall reaction for what's happening at those electrodes. Tin ions becoming purified tin, and the other electrode I see oxygen being generated in 4 hydrogen ions. Interesting. I always remember reduction happens at the cathode and oxidation happens at the anode. And this reminds me and brings me to Faraday's law, which I have another video for, so I might not spend much time on it right this minute. But it is to say that it's pretty easy to count the number of electrons transferred in terms of the flow of the amperes or amps of electricity. So, since I have another video on this, I might not spend much time on scrolling quickly through it. But just to say that if I count number of electrons flowing and count the amperes and time it as in terms of number of seconds it happens, then I can use in industry. Here's a blurry picture, but it's a big room of purifying copper through electrolysis, where they take the impure copper over here at the anode and they push it from the solid phase into the aqueous phase, losing electrons, and the copper ions and generated right here travel through, in essence, they travel through solution and are plated onto this electrode. This electrode grows heavier, and this electrode goes lighter, and the purified copper that I create over here as a reduction, through reduction, is a lot more pure. The impurities sink to the bottom and are left behind, and this electrode gets 99.99% pure. And in my video on moles plated, moles generated, you can maybe practice this some more, but I do say memorize this equation, but I'm not going to go into it right this minute, am I? No, I'm not going to. But I'll say if I know the current, and I know the time, I know the number of electrons transferred, and I know Faraday's constant, it's pretty simple to find out the number of moles of substance, pure element, usually generated in that electrolysis process. Sweet. The end. See you soon.